Hello and welcome back once again. In the previous lecture, we discussed about fatigue failure and learned about different aspects of fatigue such as types of stress cycles, different ways of presenting the fatigue data and so on. In this lecture today, we are going to discuss about fatigue crack initiation and growth. The fatigue process can be divided into the following stages. First, crack initiation. Number 2, slip band crack growth. Three, crack growth. And finally, ultimate fracture. As far as crack initiation is concerned, it is generally found that fatigue cracks initiate at a surface. And when it is initiated in the interior, generally it will be forming at an interface such as the interface between the parent material and a second phase. Okay, so that's the typical characteristics of a fatigue crack. Now, deformation during fatigue is similar to the deformation that happens in static loading in many ways, particularly the fact that fatigue deformation can also occur along specific crystal planes and directions. However, sleep in fatigue is not as widespread and uniform as in static deformation. So in fatigue, while sleep lines will be observed in some grains, other grains will be free of such sleep. These sleep lines generally form during the first few thousand cycles of stress, and during the successive cycles, sleep bands form. Okay. Now, some of the sleep bands will be more persistent compared to others. And these persistent sleep bands are actually the embryos for fatigue cracks. Okay, so once the crack forms, it will first propagate along the sleep planes, although later on it can take other directions normal to the maximum applied tensile stress. And fatigue crack propagation is generally transgranular. So we have covered these two steps, crack initiation and sleep band crack growth. Now, if you look at the mechanism as to how the crack forms or the mechanism of fatigue damage as such, it basically involves what is known as slip band extrusions and intrusions. So let us talk about this as to how the extrusions and intrusions form during fatigue deformation. Now, if you compare this with the static deformation, in fatigue, the slip bands are the result of build-up of fine slip movements of the order of 1 nanometer. Contrary to steps of 100 to 1000 nanometers in case of static deformation. And in terms of the basic deformation mechanism, if you see as to how the slip bands grow, in the static deformation process, it will basically lead to formation of a contour at the metal surface, and that can be depicted through this picture. So in static deformation, this kind of contour will form on the surface of the material. But due to the back and forth slip in case of fatigue because of the dynamic loading condition, it will either lead to formation of a notch or intrusion or a ridge or extrusion, and that can be depicted by this diagram. So due to back and forth slip movement, it can lead to formation of a notch or intrusion like this. Or it can lead to formation of this kind of ridge or extrusion. So a notch like this can be a stress riser, and hence can lead to crack formation, which is true for the ridge also. Okay, so that is how the crack forms in case of fatigue deformation, in contrast to the static deformation where it is only a contour that forms on the surface of the material. Okay. Now coming back to the stages of fatigue as we listed in the beginning, the slip band crack growth, which involves deepening of the initial crack on planes of high shear stress, is called stage 1 crack growth. The growth rate in stage 1 crack growth is very small, of the order of nanometer per cycle, and crack growth on planes of high tensile stress, that is stage 3 of fatigue, is known as stage 2 crack growth. This involves growth of a well-defined crack in the direction of normal to maximum tensile stress. Okay, and the growth rates here are much higher compared to the stage 1 crack growth, and this could be of the order of micrometer per cycle. And the other difference between stage 1 and stage 2 crack growth is the fracture surface, which is featureless in case of stage 1 growth, but in stage 2 growth, specific features known as fatigue fracture striations develop on the fracture surface. These striations basically appear as ripples like this. If I show it through this schematic, something like this, where each striation represents the successive position of an advancing crack front that is normal to the largest tensile stress. Presence of the striations on the fracture surface is a confirmation of fatigue failure. However, their absence does not exclude the possibility of fatigue fracture. Now, the other notable characteristics of stage 2 crack growth is that the crack propagates by a crack tip blunting process. And this can be shown by the following diagrams. So at the start of the loading cycle, the crack tip is sharp, as you could see from the first diagram over here. And as the tensile load is applied, the small double notch that you have at the crack tip concentrates the slip along planes at 45° to the plane of the crack. That can be seen in the second diagram here. Now, as the crack widens, it grows longer by plastic shearing, and at the same time, the tip becomes blunter. Now, when the load is changed to compression, the slip direction changes and the crack faces collapse, and new crack surfaces created during tension is forced into the plane of the crack. Okay. So now in the cycle there is tension and compression. So this was during tension. Now as the slip direction changes in compression, the crack faces are crashed together, right? Because of the change in the direction of the load. So that's what you can see here in this diagram now. In this situation, the crack partly folds by buckling to form a resharpened crack tip as shown by this diagram now. So this resharpened crack tip is now again ready to advance and be blunted in the next stress cycle. And this cycle continues, and that is how the crack propagates by this crack tip blunting process. Right, so this is how the crack propagates in the stage 2 crack growth process. The crack growth in fatigue can be defined by the crack growth rate dA by dN through an expression like this, where A is the crack length, sigma A is the alternating stress, A is a constant, the value of P ranges from 2 to 4 and Q can be in the range of 1 to 2. This can be also expressed in terms of the total strain through an equation like this. But the most common way of expressing crack growth in fatigue is through a plot between stress intensity range delta K and dA by dN. Delta K is given as K max minus K minimum, where K is the stress intensity factor which can be also expressed in terms of the stress and the crack length, because K is equal to the stress sigma into square root of pi into A. So therefore delta K will be sigma max square root of pi A minus sigma minimum into square root of pi A, which can be also rearranged to write it in terms of the stress range sigma R, because sigma max minus sigma minimum is equal to sigma R. Okay. So if you take a plot between dA by dN and delta K, the plot will look like this. This will basically give rise to a sigmoidal shaped plot. This is on a log scale, and this gives rise to a sigmoidal curve like this. So in this plot, there are basically three regions. Region 1, region 2, and region 3. Region 1 is bounded by a threshold below which no observable crack growth is obtained. So below delta kth, the crack behaves as a non-propagating crack. Region 2 is the linear region, which is also known as Paris law and is expressed by this equation. Okay, so a log-log plot of this equation will give rise to a straight line, the slope of which is m. Okay. Region 3 is characterized by rapid crack growth, when K maximum approaches Kc, which is the fracture toughness of the material. And the typical characteristics of this curve that you should note here is the fact that the crack growth rate depends on the stress ratio R. Increasing the R generally increases the crack growth rate, and the dependence of the growth rate dA by dN on R can be expressed by this equation. Okay, and generally the effect of increasing R is less in region 2 compared to that in region 1 and 3. Okay, so that was all about fatigue crack initiation and growth. And with that, we come to the end of this lecture. Thank you for your attention.